Hi guys. So what we're going to do today is we're going to look at the dot product of some two vectors, and then we're also going to look at some applications. So dot product is a process we can do with two vectors. Looks similar to multiplication, but it is going to involve multiplication. It's going to have one more step than that. So right here, this is your formula for dot product. Okay, so if u and v are two vectors, the dot product is going to be where I take the horizontal components of both vectors and multiply them together. Then I take the vertical components of both vectors and multiply them together, and then I take those two numbers and add them together. So one thing you guys will notice when we actually solve for dot product is that our answer is actually not going to be a vector. The answer is actually going to be a real number, a whole number, a scale, not necessarily a whole number, but it's going to be a scalar factor. So if there is one other application of dot product, if that dot product works out to be 0, that actually tells us more about the vectors. If that dot product is 0, that means those two vectors are perpendicular. Another word you'll hear for perpendicular when it talks about vectors is orthogonal. So we can determine if two vectors are orthogonal by looking at the dot product. Okay, so we're going to look at an example here to try and determine dot product. And it's actually going to be a pretty simple process if you can remember what you're doing. Okay, so we're going to find the dot product of the two vectors shown here. So I have two vectors, w and v. So I'm going to find w dot v. And what's nice here is it doesn't matter the order. W dot v is going to be the same as v dot w. But what I'm going to do is I'm going to take the horizontal components and multiply them together. So I'm going to do negative I, which is just one I. So I'm going to do negative 1 times the horizontal component of v, which is 3. Then I'm going to add that to the vertical component of w, which is 4, times the vertical component of j, which is negative 2. Then all I have to do is the math here. Multiply first, that gives me negative 3 minus 8, which gives me a final answer of negative 11. So the dot product here, w dot v, is negative 11. Again, it works out to be a number, not a vector. Okay, so hopefully dot product is pretty simple for you guys, but we actually have another application of this that we can use. Now, the dot product actually gives us another formula that's based off of the law of cosines. I'm not going to go through the whole proof here with you guys, but this formula here that's in that red circle, okay, this is going to be another thing we're going to use. That formula is going to help us to determine the angle between two vectors. Okay, so for example, if we get this picture, I have a vector here that's A, I have another vector here, it's B, they're both coming from the same point. I'm going to be able to find that angle between the two of them by using this formula that's in the red circle. Okay, so let's go ahead and try an example of that and find the angle between two vectors. So I'm going to use the same two vectors I just did. Okay, I've got negative 1i plus 4j, and I've got 3i minus 2j. And if you look over there written in purple, that is the angle in between. We're going to determine what that is. So I'm going to set up this formula. So I know that cosine theta is going to equal v dot w, okay? We already know that answer. We just solved it a second ago. It's going to be negative 11. But again, if you don't remember, I do the horizontal times the horizontal plus the vertical times the vertical. So my dot product is negative 11. Then I have to divide that by, if you guys remember those two double bars, that means the magnitude of v and the magnitude of w. So let's go ahead and determine what the magnitude of each of those is. Okay, so I'm just going to show that down here, away from the problem I was just working on. So the magnitude of v, actually let's do w first, since that's written first. So the magnitude of w, that is the square root. It's based off the Pythagorean theorem, if you remember. I take the horizontal component, and I square it. I take the vertical component, and I square it. And I add those together, and that gives me the square root of 17. So the magnitude of w is the square root of 17. And even though the formula there says magnitude of v first, it's okay to reorder it because you can multiply in any order, okay? So I'm going to go ahead and write square root of 17 there. Then I also need the magnitude of v. So the magnitude of v is the square root of 3 squared plus negative 2 squared. So that would be the square root of 9 plus 4, which would be the square root of 13. So the formula that I get is cosine theta equals negative 11 divided by the square root of 17 times the square root of 13. Now that is a lot to do without a calculator. It is possible for these to be nice, easy, exact values that you can work out without a calculator, but that's not always going to be the case. So we're actually going to want to use a calculator here to evaluate this. So go ahead and get a calculator out and make sure we're trying to find this angle in degrees, so make sure you change your mode to degrees. And if you guys remember from what we did earlier this year, in order to find the angle here, we have to take the inverse of what I have. So to find my angle, theta is going to be cosine inverse of negative 11 over the square root of 13 square root of 17 square root of 13. Just be careful with your parentheses here. Make sure you're dividing by both the square root of 17 and the square root of 13. And if you do this correctly, you should get, I believe it's 137.7 degrees, but let me double check with my calculator because I can't do this without one. And yes, it is 137.7 degrees, and that is the angle between those two vectors. Okay, so dot product helps us do a couple things. It helps determine if those vectors are orthogonal. So for example, these two were not because the dot product didn't equal 0. It also helps us find the angle between two vectors. Now those two things also go together because if you think about that, if the dot product were 0, if I was doing cosine theta of 0 divided by anything, doesn't matter what that is, I'm going to be doing cosine theta equals 0, which always ends up being cosine inverse of 0. And we know that that's 90 degrees, which means that those vectors would, again, they would be perpendicular or orthogonal. All right, the last thing we're going to look at is just some applications of vectors, some word problems, some situations that involve them, and some things they can help us with. So you may have seen some questions similar to this in your physics class, but we're going to go ahead and do some examples in case you haven't seen something like this, if you've seen them in different ways, or for those of you who are in chemistry right now and have never seen this before. So what we have, there's a Boeing 737 aircraft. It has a constant speed of 500 miles per hour, and it's headed due south. So we're going to go ahead and draw this picture. So I have a plane, and it's heading due south. Then I also have, there's the jet stream that is 80 miles per hour in the northeasterly direction. So I'm going to try and show what these two vectors would look like. I've got one going down at 500 miles per hour. Then I have one that's going up northeast at 80 miles per hour. So I know that's 80, and this is 500. So what I'm going to do to start is I'm just going to find what these two vectors are, what these are in terms of I and j. So I'm going to start with the velocity of the 737, okay? So ignoring the jet stream, we're just going to find the velocity of the 737. And if you look, there is no horizontal component to that vector. There's only a vertical component. And if we say that north is going up and north is positive, that means since it's going 500 miles per hour south, then we're going to say that the velocity of that jet, or we'll say the velocity of A for airplane, would be a negative 500 j. So there would be no I because there is no horizontal component. All right, then we're going to try the velocity of the wind, so VW, or the jet stream, I'm sorry, in this case. That's going northeast. So since it's northeast, there is both a horizontal and a vertical component to it that we need to determine. So remember to find that, to find the horizontal and vertical component. It's dependent on the angle. So the horizontal would be the cosine of the angle. If it's northeast, that's going to be 45 degrees. And I multiply that by the magnitude. So the horizontal component would be 80 cosine 45. The vertical component would be 80 sine 45. And if you remember your exact values, sine and cosine are going to be the same thing. The sine of 45 is 1 over root 2. So that makes the horizontal and the vertical component both 80 divided by the square root of 2. So I have 80 over root 2i plus 80 over root 2j. If you want to, you also could rationalize your denominator, and that would be 40 square root of 2. That's the same thing, but I'm going to save that step here and just leave it here. Okay, so the next thing we're going to do is we're going to find the velocity of the 737 relative to the ground. So what we have to do there is we actually have to add these two vectors together in order to determine what that's actually going to be. Okay, because we know if we have that jet stream that's pushing that airplane, we're actually going to be looking not at that perfect negative 500J vector. It's actually going to be something more along these lines because we have that jet stream that's a factor. So in order to solve it for what that's going to be, we're going to take those two vectors and we're going to add them together. So we're going to take the velocity of the airplane, add it to the velocity of the jet stream. So what I have there, I have the horizontal component. There is only one horizontal component here. And that's going to be the 80 over root 2 I. Then I have two vertical components I do need to add together. I have the 80 over root 2 J from the jet stream. Then I also have the negative 500 from the airplane. Now, if you want to type that into your calculator at this point to get a decimal, that's okay, because for what we do for these next two parts, it's not going to be an easy exact value. We're actually going to have to get into some decimals. So if you want to do that, you can write that as, let's see, that's 80 divided by the square root of 2 minus 500. So that would be a negative 443.4J. All right, so this right here, that vector, is the answer to part B. So the velocity of that vector, I'm adding those two components together. Okay, and that's the green line that I drew over here in my picture. It has a horizontal component that's positive, because if you think about your XY axis, that's where they would be. Okay, so that is a positive horizontal component, but it's also a much smaller component than the vertical, and that vertical component is in the negative direction. All right, the last thing we're going to do is we're going to find the speed and the direction of that 737. So we're going to use our answer from part B to determine those two things. Now, in order to find the speed, what I'm going to do is I'm going to use the magnitude. So what I'm going to do is I'm going to take the magnitude of VA plus VW, and let's just call that VG, because it's the velocity V sub G. Sorry, there we go. Because that's the velocity in terms of relative to the ground. So in order to find the magnitude, it's going to be the square root of those values squared. So 80 over root 2 squared plus 80 over root 2 minus 500 squared, and this is when you're definitely going to need a calculator. So go ahead, type this in, find your value for the velocity, and that should work out to be, we'll have to estimate here and round that, it's going to be about 447 miles per hour. So that's the effect that the jet stream is going to have here on my velocity. Okay, then the last thing we want is we want to find the direction. Okay, so what we're going to do is we're going to try and find that angle here on my vector. So again, that vector has a horizontal component and a vertical component, which we found. Okay, that vertical component is the 80 over root 2 minus 500. The horizontal component is still the 80 root 2. So what I need to do then is find that missing angle. So I'm going to use tangent. So the tangent of theta is 80 over root 2 minus 500 divided by 80 over root 2. And again, you're going to want to use your calculator here. We're going to do tan inverse in order to get our final answer. And that should work out to be a negative 82.7 degrees. All right, now the last thing you might see is just a different way to write that angle. It is a negative 82.7 degrees if I start at 0 and go backwards, negative 82 degrees. But when we're referring to things in terms of north, east, and south and things like that, we won't see it written as a negative 82 degrees. The way you would see that written is that it's 7.3 degrees east of south, so you'll see it written as this if you were to look at it in a textbook or something along those lines. You don't have to get to that last step, that's okay. If you just get to here, that's fine. but I just want you guys to know what that looks like because that is something you may see in a book or something else along those lines. All right, so that's all we have on vectors for now. We're going to look at parametric equations over spring break, which are going to use some similar components here. So hopefully this is just an intro to really help you guys be able to understand those parametric equations a little bit better after the break.